Welcome, everyone. Thank you for coming. Today, we're going to give you a presentation on compute-based sizing and operation dashboard to share with the lesson learned and how we are using big data in our company. Before we start the topic, let me give you a quick introduction about us. My name is Janet. I work for HP, come from Austin, Texas. And I've been managing internal and external teams of architects, database administrators, and infrastructure providers to deliver big IT projects. My recent project I'm working on is I'm the lead of the Hortonworks cluster we created and used by HP IT as our data lake. And this is Pranay. He's from Hortonworks Professional Service. Pranay is a big data architect and engineer. He has been helping us to build a cluster for us. And as part of the project we worked on in the last 1.5 years, we learned a lot on both infrastructure and application side. So during today's session, we're going to share with you our learning on how to do the compute-based sizing using our operation dashboard. This is our agenda. First, we're going to tell you why we need to do a sizing and what is the approach and the challenge we faced during the sizing exercise and what is the solution. And also, we come up with a set of framework and the toolkit to help us to reach the goal. At the end of the session, we're going to do Q&A, but please, if you have any question, just let us know. We want the session to be very interactive. Okay, let's get started. Sizing puzzle. I will talk about why we need to do the sizing and what are the challenges we are facing to come up with a compute-based sizing instead of the traditional storage sized. And also, what is the approach for us to come up with our solution. Why do we need to do sizing? First, we want to give you a background on this platform we built for HP. So it is central data lake for the entire HP IT. It is very critical for a lot of business units like our supply chain, sales, finance, our customer service. They all rely on the data from this lake. And also, the key point here is the beginning of this project it's a data transformation. We're replacing our legacy EDW data warehouse into this big data platform. So all the data will be loaded into this lake. Then we're going to do a lot of data processing, then load the data into the reporting zone on the public cloud for the business to use it to create a business report. With a lot of data hosted in the lake, and a lot of workload running in the system, it is very important for our success to define our sizing, the right sizing, and also make sure the job performance, it's not too slow because of the lack of compute. At the very beginning, we realized right away that the traditional storage sizing is not going to solve our problem. We need to find a way to find the right sizing and to make sure the SLA is met with the right size of the cluster. And it is not straightforward. We faced a lot of challenge during the sizing exercises. I want to show you a few. The first challenge we have is this is a multi-application. We all know there's a lot of challenge when you have multi-task application in the same data lake. We already have 11 big programs running in and using the lake, and we'll continue having more application, more big program come in, use the data hosted in the platform. When it comes to sizing, each application have their own SLA, they have their own end architect they want to achieve. And how do we meet the need and make sure we have the SLA is our first challenge. The second one is this is a lake not only hosting data, it does a lot of transformation. We have data from the raw data side, from our own HP internal service bus. We have the data, like have 10 years history data loaded into the system. And also we have data from Oracle database. We basically put all sort of data, move them into the loading zone. Then we do data transformation, and prepare the data into the data pipeline, then eventually put them to the public cloud to, for the business user to do their business reporting. And also I want to highlight this environment, like most of our data lake is on-premise in our HP data center, but also we do have that ad hoc one-time offer for the cloud, the platform on cloud. We're using CloudBreak. So we can quickly spin up a cluster for business, for application, for them to do performance testing, to do UAT testing, to do before they go live to production. The moment they go live, we will shut down those cloud environment. Our central lake is still on-premise. So this is a challenge for us, like when and how we're going to put a quick environment on the cloud, and when we're going to decommission the cloud environment so we can meet the requirement, we can give business the data they need very quick, very fast, but also have the cost in mind. The next challenge I want to bring up is, how do you know what is the right size, how much memory, how much CPU you need for your cluster? Of course, you need to ask your application, your business, but in this case, like I said, this is a transformation. A lot of application came from the old traditional EDW environment. They do now know once the data is processing using high, what is the RAM they need, what is the young memory they need. So we have to come up with a compute method, a strategy, the tool ourselves in order to decide what is the right size for the cluster. And next one is, for the application we know, we study them, we predict the usage, and we can give a 3 years projection. But for the upcoming application, how do we know how much compute they need, what's the data size they need? Is a challenge for us. As part of this task, we need to come up with a tool and for new application onboarding to say, hey, when you come, we know 3 years, what is your need for the next 3 years. Yeah, so the last one, and this is most challenging we're facing on the technical side, is we have this environment that is workload. It's very it's region-based. A lot of application will have the same spec. They all load the data at the same certain time of the day. So you will see most of the time the platform usage is flat, but at a certain date and time, it will have a peak. So how do we handle this peak time? We cannot sizing the cluster based on the peak because it's a waste, but also we have to find a way to make sure the performance is not going to be degraded because of lack of compute. So with all this challenge in mind, this is our approach. Of course, we first study what we know. We talk with each application to understand what their footprint, what is the data volume, and what is the need, what is their SLA. With all those information in hand, then we have to come up with to study the workload. We spend a lot of time to look at the compute-related data, especially during the peak workload, like what is the CPU usage, what is allocated peak RAM usage, storage capacity, network throughput and average response time, and transaction throughput. So we spend a lot of time to manually study this workload. Then we realize we cannot just do it manually. We have to have a tool to help us to fit the need, and we can use it ongoing base. That's where we developed the internal tool called Operation Dashboard. Pranay is going to show you more detail in the next few minutes. So with that, I will hand it over to Pranay. He's going to show you what's the solution to have the sizing correctly and also the operation dashboard.
Right. Thanks, Janet. So like Janet mentioned, HP's infrastructure is complex. So basically, any major data lake environments is very complex, where you're running large amount of jobs. Like say you're running 15,000, 10,000 jobs. How will I manage what's happening in the cluster? How would I know how much memory, how much CPU cycles will I need, and whether I'll meet my SLA today, whether I'll meet my SLA tomorrow or not? So these are very important questions that, and we need a framework around this that helps us in doing a compute-based sizing. And that's where we came up with this idea. Now, just to go a little background, like any other data lake environment, the data comes into the system as we store it as a raw data. Then we do a historical, there's a historical layer where the data, history of the data is maintained. And there is a transformation layer where you join multiple historical tables, create a transformed data sets. And through that transformed data sets, you also create a reporting data set, which eventually is moved out to visualization tool on cloud. So this is the basic standard ELT process that HP had been following. And the main idea about coming up with a compute-based sizing is to have a base run, to do an initial run, and collect the metrics for the initial run that follows through the loading, history, transformation, and reporting. And once you have collected the metrics for your jobs through all these layers, we can extrapolate based on the number of jobs that we are going to create, we can extrapolate the amount of sizing and computation power that would be needed to achieve the SLA that we are trying to target. Now, there is also another thing where we do all these sizing efforts, but then we change the parameters, like say we change the container size, Hive container size, we change the yarn memory settings. Now, all these impacts how much computation power is needed. So it is important that we baseline the initial cluster settings and then do a computation power on top of it. Now, the first thing that we did, we needed a method to collect data. And that's where the operation dashboard comes into the picture, which is the second part. But assume that we have the data. I'll walk you through on how we collected the data. So once we collected the data for the initial run, we categorized the jobs based on two main factors. One is the duration, and second is based on how much computation power it needed. Like say we categorize the job, like say the job falls is a tiny job, small job, large job, and major job. And we also categorize based on the number of containers it needed, tiny footprint, small footprint, large, and major footprint. So this categorization helps in understanding where the majority of the computation power is needed and where the majority of the time is being spent. So like say if we go back a little, like say we said the ELT process, so it was very evident that between the history layer and the transformation layer is what majority of the containers were being utilized. And more of the time was being utilized in reading the historical data, getting the latest information of the records from a billion record table, billion row table. So these were our main target area on how to minimize the duration as well as the computation needed to process history and transformation layer. Now, once you have categorized these information, the next thing that we need to do is, based on our current understanding and the current sizing of the cluster, we need to understand how many jobs we can run. Now, so we had to collect some data, like understand how many total map tasks and reduced tasks are needed to do an initial run. So we had an initial phase one, where we had a set of jobs that follows through the loading zone, history zone, reporting zone, transformation and reporting zone. So we collected the total map task needed, total reduced task needed to do this initial phase one. We collected the average map time, average reduced time for each of these classifications that we saw earlier. Like say for tiny jobs, we saw the average map time to be this much, average reduced time. For a job that has a large footprint, this was the average map time and reduced time. So we collected these information. And based on the existing EDW system, which was running almost close to 600, 700 jobs, we were able to extrapolate that those jobs, when converted into Hive, it would be almost around, almost close to 10,000, 12,000 jobs that we could extrapolate. Because we had all these different layers, so overall jobs will be actually, double than the existing EDW. Now, the next thing, important factor is to understand how many map tasks and reduced tasks you can run in your current cluster based on the sizing that you had, initial sizing. Like say HPI initially had 6 terabyte of yarn memory. with configured taste container size of 4 GB and map reduce ratio of 70/30. So it's an assumption that if we are running, I'm running 100 tasks, out of which 70 would be map task and 30 would be reducer task. And based on the initial run, we could figure out that average map time before the initial run was 0.34 minutes, and average reducer time was 0.5 minutes. So I'll show you how we got this metrics, which is the important part. But right now, we'll just see how we utilize this information to do the computation calculation. Now, based on the average map time and reducer time, we were able to calculate, to run in 24 hours, in a day, based on this much amount of time, we'll be able to run almost like 4 million map tasks and around 1 million reduced tasks. So this gives us an idea like, hey, with my current capacity, this is what I'll be able to do with the clusters. Now, the next task is to extrapolate, the number of jobs at each classifications. Based on the initial run, we had, like, say, there were 2 major jobs, 5 large jobs, 20 small jobs, and 20 tiny jobs. And the expected count are what we projected that we'll be able to run. We need to run these many jobs. Now, based on these counts, we will be able to, identify the number of map tasks needed and number of reduced tasks needed to, to be able to meet those requirements. Now, with 6 terabyte, we needed almost like 4 million of map tasks. We would be able to run 4 million map tasks in 0.34 minutes and 1 million reduced tasks in 0.5 minutes. And based on the projected counts of Hive jobs, we were able to, project that, hey, if we need to run these transformation 3 times a day for US, Asia, Europe, and Asia Pacific within 24 hours of the time, we would need almost this much amount of map task and reduced task. So it was evident that the current 6 terabyte of yarn memory won't be able to meet those particular computation need that we have, and we would surely be missing our targets in terms of SLA. So next thing is, based on these calculations, we resized the cluster, and we were able to, bring the computation power almost close to 21 terabyte from existing 6 terabyte. The next main critical information is how we got this data. Because if we have the data, doing the calculation is not that complicated, but getting the data is what is the more complicated part. Now, we started looking at many ways to collect the metrics of the jobs. And the most stable way that we thought is writing our own job that gets all the metrics informations. And we can do a visualization on top of that, do this classification and everything, and then have a historical analysis on how the jobs are performing. So to do that, we created something called an operation dashboard, which allows you to do a historical analysis of how your jobs have been performing. So, and this also gives you critical information towards your platform sizing. And the main important right now that we have when we are running like 15,000 jobs in our cluster, it is important to know how my jobs are performing today, how my jobs performed yesterday, last month, and previous months compared to what's happening today. So right now, like say if I'm SLA bound and I miss my SLA, we need to pinpoint which job, which high query, what exactly was impacting my SLA for today's run. And so what we did, currently when we run any jobs, which is on Yarn and Taste, all these execution details are stored in HDFS in a location called /ATS/done. So /ATS/done directory has, has a complex JSON object. It's a JSON file with multiple JSON objects within it. And the idea was to somehow parse this information, capture the metrics, and use that metrics information to do historical analysis of how your jobs had been performing. So we wrote a custom parser. Timeline Server does this for you, but Timeline Server, we already have 15,000 jobs running on the cluster. So all the jobs are already interacting with timeline server, and we didn't want to load the timeline server more further. And then what we saw, that more you load timeline server, the more slower and more impactful it gets. So sometimes we could see that out of 10,000 jobs that we are running, only 3,000 jobs metrics we were able to capture from timeline server. So we had to write a custom parser so that it's in our control, like say, hey, give me the job details, metrics information from this date to this date. So your custom parser will be able to get those information for you. So we had a continuous script that's running overnight, captures all the job metrics information that had happened today, and then load it into a database and use a visualization tool on top of it. So what we were capturing. So what was needed at HP? There is more details that we can capture, but the main critical information that we needed at HP is the application details. What was the application ID? Which user was running it? What was the container size? Because container size we allowed to be overridden at runtime. How many application attempts were made? And going further, we were capturing the DAG details, like what was the DAG ID? What was the DAG name, the actual query that ran, the full query, the submit time, the initialization time, the start time of the query, and the queue in which the query was running. Then we were also capturing the vertices details. Like you say, every high-phase job will have multiple vertices. Like say there's map 1, reducer 3, map 4, map 7. So we were capturing the vertices details. Within each vertices, how many tasks were being spawned, what was the average task duration for each vertices, max task duration, and the minimum task duration, and the start time and end time, and the status of the vertices. So vertices could fail, vertices could succeed as well. Then we were also capturing additional DAG details that, like say, which table is getting loaded, how many records are being inserted, how much memory is being used, how much CPU cycles, how many files were written, and how much HDFS input-output commands were issued. And yeah, so these and number of vertices. So these information will help us in understanding how the jobs are performing. And we were utilizing the vertex max, min, and average duration to the compute-based sizing. Now, how this helps? Now, a sample dashboard that we say that we see here right now is, based on the classifications that we saw earlier, where most of my jobs lie. So, after performance tuning, this is what it looked like. But before performance tuning, like say for on the tiny job, right, on the category, the tiny job was small. We had a big, super large, and large jobs. What we are trying to see here is that, this gives us a visualization of where majority of my jobs are in terms of duration and in terms of footprint level. And we were able to target specifically, pinpoint which jobs is actually not performing well and which job we need to do a performance tuning on it. The next thing, like Janet mentioned, right, these are all region-based jobs and multi-tenant applications. So there is always, we could see a pattern in our job that at 12 a.m., I would see most of the jobs triggered by all the multi-tenant applications. So you will always see this peak at 12. We'll see a dip at between 6 and 9 a.m. And again, there will be a peak after 12 p.m. So we could see that the jobs are being triggered all at the same time. And this helped us in understanding, should we size based on the peaks, or should we size based on, how should we size the cluster? That was always a bigger discussion. So it was always then we took a decision that we cannot size based on the peaks, and we cannot also overlook, that the computation power is needed at the peak time, because the jobs has to start at 12 a.m. There's no other go, because they have to complete their cycles. And we could also observe many interesting parameters at this time, right? During max parallelization, we could see the number of jobs running are more, but the computation power required was less. This was happening during the loading layer, when we are moving the data into loading to history. And we could also see another pattern where, we could see max resource utilization, but the parallel job set are very less. This was happening at the transformation layer. So we could see what's happening and how the cluster is behaving at different kind of patterns and different kind of load jobs. Another main important, important feature of this particular parser is that it allows you to do a historical analysis of your jobs. Like say I have 5,000 tables, and how do I manage it? So you could select a table and see the historical load patterns, and you can see how many records are loaded today, yesterday, in overall period of time, how much CPU cycles, how many vertexes, how many tasks it took to load it. And you could also see like for example, if there is a change in vertex, like say my job always runs with 3 vertex, map 1, map 3, and a reducer. So it joins 2 tables, and then there is a reducer that combines it and writes the output into a table. Now tomorrow, all of a sudden, I see there is another map or another reducer task, or there is no reducer task. Now so you can see a pattern. Like say if number of vertices changes, that means my explain plan has changed. And if an explain plan changes, then there is a deviation in terms of duration, number of tasks, and everything. So this helps you in pinpointing what exactly happened. If the number of records being loaded into a table should fairly be among the same time, so you will have a rough estimation on how many records are getting loaded. And if you see a sudden dip or sudden rise in number of records for a day, that means you're probably getting a bad data. And same thing is with other memory utilizations and everything. So overall, this dashboard or that we were using for operation dashboard helped us, in not only doing a compute-based sizing, but also to do a platform, application monitoring, see how jobs are performing over a period of time, helps the developer and the support team, to find a root cause on why SLA had missed or why we met an SLA on that day, right? So this we found that's something very critical, and it helped us a lot in terms of which jobs to performance tune, which jobs to concentrate on, and which jobs to change. Next, I'll leave it to Janet.
Thank you, Pranay. Like Pranay demo, this dashboard is very important. We use it. We started with sizing need, but then now it's used for our operation team as an operation dashboard, so they can monitor job on day-to-day basis, and also we use it as a performance tool as well. So I would like to share, summarize what has been covered, and also more importantly, what are the takeaway along the sizing journey, what are the tools and framework we put together to help us going forward. Here's a quick table. It's very small, but it tells us the delivery we do as part of sizing solution. So for the new application onboarding, we have created the infrastructure assessment tool, as well as application assessment with a template. So we have the application questionnaire and checklist for each new application coming to this data lake cluster. We have the sizing calculator for the new application, especially on the young memory and the HBase. And for the ongoing project application that is using the platform, we have operation dashboard and the chargeback dashboard, so we can charge back the application who's using the platform. We also use our sizing template and so we can perform the quarterly sizing review to make sure we have the right sizing for our 3 years platform roadmap. So sizing is part of the roadmap, so we can make sure our platform is always have the right size in the next 3 years. Last but not least, like I said, we spend a lot of time on this operation dashboard. It is can be found in the GitHub. It's open source. This it works for HTTP 2.6 because that's where we have our dashboard deployed into. And please feel free to go there, download it, and play with it, and use it for your sizing. think that's it. Any questions? I think we're right on time, but we'll be here for a little bit for any questions you have. Thank you.
Thanks.